I'm Riana Rossouw. I manage the XRF and ICP-MS unit. Before we start, I would like to introduce the rest of my team. So in charge of XRF and mineral separation is Marley. In charge of solutions, ICP and CH&S is Charney. And our mineral separation wizard is Rossouw. So let's look briefly at how your samples could have been processed for ICP analysis. So comparing solid and liquid samples, your solid sample could have been dried, sieved, or grinded to a very fine powder before it was digested and ready for ICP analysis. Or you can have a liquid sample that was either digested, filtered, acidified, or simply diluted for ICP analysis. So looking at ICP measurement, almost all of the elements on the periodic table can be analyzed. It just needs to be extracted from samples to be presented in solution form. As discussed in the sample prep lecture, a number of things could cause contamination of your samples during both the sampling as well as preparation process, such as the sampling tools, your sample containers, and the acids used. During measurement, we have to take additional care to prevent any contamination. So within the work environment, we have a laminar flow bench where we have the autosampler and prepare all of the standards. In the lab environment, there is no corroding metal surfaces. We've got sticky floor mats, shoe covers over our shoes, and we wear gloves when handling your samples and preparing standards. Our reagents for any dilutions or preparation of standards is only trace grade acids, either nitric or hydrochloric acid. All of our containers are LDPE. They are acid clean for the preparation of standards. We don't use any glass as they add a lot of contaminants, either some major elements, potassium and sodium, as well as some trace elements. The analyst can also wear coveralls if it's a very clean working environment, hoodies, gloves, shoe covers. That is standard in our environment anyway. When your samples need filtration, we rather centrifuge the samples because there's no additional contamination that can be added. Within the digestions, if we prepared all of your samples, they are all digested with microwave digestion, where all of the containers is Teflon, so there's no additional contamination from glass tubes. All our measurement tools, we use disposable pipettes, pipette tips, again just to minimize any contamination. So the ICP equipment within our laboratory, we've got a thermo ICP AES plus its own autosampler, as well as an Agilent 7900 ICP-MS with its autosampler within the laminar flow, just because it creates a much cleaner work environment. So let's look at all the steps involved from when the sample is taken up until we can report a result. The analysis process is completely automated, so all the samples to be measured is placed on the autosampler from where it is pumped to the ICP. Typically less than 2 ml of sample is used. The first part of the sample introduction system is the spray chamber, where the sample mixes with a high pressure argon gas stream to form a fine mist. Large droplets drain away while small droplets are carried to the torch. In this video you can see how fine the sample mist is, which is continuously pumped to the instrument until the analysis is completed. The fine droplets carried with argon from the nebulizer into the torch and the argon plasma at 6,500 Kelvin, where the sample is dried, atomized and ionized. Up to this step the process is the same for both ICP AES and MS. Let's look at how excitation of the analytes happen in the argon plasma. For both ICP AES and MS, a high intensity energy source is required. In atomic emission, you have the energy source from the plasma, which promotes an electron to a higher energy level, which is the excitation step. The electron falls back and emits light at a characteristic wavelength. The light emission intensity is proportional to the elemental concentration. In mass spectrometry, again you have a high intensity heat source which ejects electrons from the outer shell, which is the ionization process. The result is a free electron and an atom with a positive charge. The ions are extracted into the mass spectrometer, where the abundance of each ion is proportional to its concentration. So the detection of an element depends on its ionization potential. The ionization potential is the amount of energy required for that element to form an ion. The higher the ionization potential, the more difficult it is to ionize and the lower the sensitivity. Elements that ionize easily generates a lot of ions even at low abundance, so they have very good sensitivity. If the element has an ionization potential higher than argon, it is not ionized in the argon plasma, example helium, fluoride and neon. So what happens when a sample containing a number of elements is pushed into the high temperature argon plasma? All elements in the sample is dried, atomized and ionized simultaneously, some more effectively than others. Each element has one or more natural isotopes, all forming simultaneously during ionization, but at different abundance levels. Example, when a sample with copper is introduced, two different ions of copper is formed, copper 63 and copper 65. They've got the same chemical but different physical properties, and they have different abundances. In the AES, the same process of atomization occurs, but here the light emission from the excited electrons are of interest. In a radial instrument, where the torch is upright as on our instrument, the area of interest is zone 3 on the image, while on the MS, ions are extracted from zone 4 in an axial instrument. Detection in the AES plasma. In the thermo ICAP instrument, light emission from the excited elements is captured from the side of the plasma. So it's extracted into the rest of the instrument. It's dispersed into its different wavelengths and recorded as pixels of different energies by the solid state detector. So here's the detector itself, and here is a pixel map of some elements detected during measurement. A lot of overlapping spectra of many elements is generated, but the software is able to select at least one wavelength for each element that is not overlapped by the spectra of another. So you can see here is a wavelength position for silica that is not overlapped by any other spectra, while this specific wavelength of silica has actually another emission line of silica imposed onto the side of it, so it's difficult to separate the two line spectra. So back to the MS. In the argon plasma, every single element in your sample has now been ionized from the analytes you are interested in, along with the matrix elements of possibly high alkalis, sulfur, phosphorus, the elements from the digestion acids such as nitrogen and chloride, and all of the hydrogen, hydroxide and oxides in the sample medium. This soup of ions are then sucked through a set of metal cones with a 1 mm followed by a 0.4 mm opening. All the neutral species and light photons are rejected and do not continue further into the instrument. Complex processes within the plasma can cause some ions from either the sample matrix or the gas environment to combine and form large new molecules with the same mass as an analyte to be measured. These are called polyatomic interferences. When identifying interferences, you have to consider the isotope masses of all the ions and see how they add up to know on what element mass they will interfere. For example, in sodium-rich samples, you could have sodium at mass 23 plus argon at mass 40 to form an interference on copper 63. Molecules from the instrument gas environment can also interfere on an analyte mass. In the same way, you will have argon 40 plus oxygen 16 to form an interferent on mass 56, which is iron. The instrument have no way to know which contribution of the signal measured on mass 63 can be attributed to copper or which part is related to the interferent. You have to separate the interferent from the copper in order to do an accurate measurement. Another type is isobaric interferences, where different elements have isotopes at the same mass. So, for instance, titanium, vanadium and chromium all have isotopes at mass 50. But they each have another mass without any interferences, namely titanium at mass 49, vanadium at mass 51, and chromium at mass 52. Minimizing interference effects is important for accurate measurements. It can be done by either optimizing the instrument settings to minimize oxides and any doubly charged species. You can use collision cell technology for interference removal, or you can choose isotopes that are free of interferences. So for samples that's got high sodium, you can alternatively rather measure copper on mass 65 and not 63, as this will not have the same sodium-argon interference. In order to remove interferences, ICP-MS has a small cell filled with helium through which all the ions pass before it goes any further. The principle of interference removal is that in a small space pressurized with helium, the larger interference molecules, argon chloride in this example, are 99.9% guaranteed to all collide with the helium molecule, which will slow them down, while the smaller analyte ions, namely arsenic, will collide less with helium and have a higher velocity. The cell barrier will then only allow ions at the specific velocity of the analytes to pass, while the slower interference are stopped. A specific voltage exists for all analytes of interest, so they are sequentially let out of the cell at the time the instrument wants to measure them. In ICP-AES, there is no instrumental filter for interferences, so when no interference-free emission line exists for an analyte, mathematical corrections have to be done. After interfering molecules have been removed in the collision cell and the analytes exit, they pass through the quadrupole mass analyzer, where different voltages is applied that stabilizes only a single isotope mass at a time and pass it onto the detector. Therefore, a very fast sequential process with measurement as low as every 0.01 second, but for better sensitivity, longer counting times of 0.1 second is used. Complete analysis of more than 40 elements, 3 replicates each, can take less than 15 seconds. In order to use the output from the ICP instruments, the signal intensity generated during ionization of each element needs to be converted to a measurable quantity. Instrument response is calibrated using multi-element standards measured at different concentration levels to generate the calibration curve, which should be linear for all elements over the concentration range of interest. With the response curves for each element, you can, for instance, relate the signal intensity of 2000 counts per second for cadmium to a concentration of 780 ppts. Some important guidelines when making up the standards for instrument calibration. So we typically need 4 to 5 standard levels, one above and one below the expected range in a matrix similar to the samples. Standards are prepared from NIST traceable certified standards. It's easiest to prepare from a multi-element stock instead of adding single elements together. We use high purity trace element grade nitric acid as well as hydrochloric acid and deionized water to make up the standards, usually in 2% nitric acid and 0.5% HCl. Standards are prepared in acid-cleaned LDPE or polyprop containers, no more than 50 ml volume as the standards cannot last forever. Concentrations above 10 ppb is stable for up to 6 months. Lower levels are usually prepared daily. The sample matrix as well as the acids used for digestion can all result in matrix effects during measurement, which will affect the accuracy of the results. Changes in acid concentration and acid type have an appreciable effect on analyte signal. difference in physical properties lead to changes in the nebulization process, affecting the rate of analyte injection and therefore the sensitivity. If we look at aluminium and manganese, you can see how the signal changes in different types of acids. So at different concentrations of hydrochloric acid, at a low concentration you'll have a high signal intensity for both aluminium and manganese, where up to 50% HCl, manganese has a significant drop in sensitivity, aluminium just a small amount. If you compare this to an acid like sulfuric acid, the high concentration of acid up to 30% sulfuric acid leads to a very significant drop in sensitivity for manganese as well as aluminium. When looking at different concentrations of acids just simultaneously, so phosphoric and sulfuric acid causes the most significant drop in sensitivity, while nitric acid is the preferred acid for measurement, as it results only in a small amount of signal loss as the concentration increases. Knowledge of the total dissolved solids or volatile and carbon content of liquid samples submitted for analysis should be known, as it changes the plasma energy and ionization potential. High alkali concentrations lowers the ionization efficiency of the plasma. It lowers the signal intensity of the analytes of interest, and accordingly results will be too low. You can monitor the color of the plasma to quickly identify high analyte concentrations. Watch what happens when we aspirate a solution of 1000 ppm yttrium. So normally you will just have the plasma at a light green color. As soon as you introduced high concentration elements, the tail of the plasma will just turn a bright orange color. Volatiles, example alcohol in wine, or high carbon content of biological material enhances ionization efficiency of some elements, for example arsenic and selenium, and they will show results that are too high in your samples. High salt content also results in salt deposition on the ICP-MS cones, which will cause instrument drift over time. So the cone on the right is a fairly new nickel plated sampling cone. The cone on the left is a copper based cone which has been exposed to high concentrations of salt from sediment digestions, so it's got a lot of carbon and salt deposition on the cone surface, as well on the tip of the cone, which will result in signal drift over time. Apart from either diluting samples to reduce total dissolved solids, which could affect detection limits, unfortunately, or setting a more robust instrument conditions, which will also result in the instrument being less sensitive, an efficient way is to use internal standard elements to correct for matrix effects. A single or multi-element mixture of elements which cannot be present in the samples, or they cannot add any new interferences or contaminants, are added simultaneously to both samples in standards using a mixing tea. This is continuously added throughout the whole sequence. A plot of these elements over time indicates instrument stability. So if from the start of the analysis up to the end of analysis, the relative standard deviation of the internal standards changed very little over time, so there didn't appear to be a lot of signal drift during this specific analysis. The amount of drift, had there been any, could have just been corrected by applying the same amount of drop in signal intensity as a correction to the results. So as I mentioned, the internal standard shouldn't be present in the samples. So here is a sample that seems to have a high amount of probably scandium and yttrium. Same for these samples. So if a correction will be applied using yttrium as a correction, it will completely undercorrect the results by applying a reduction of signal intensity to the measured analyte, and the results will be too low. This part of the sample sequence shows samples where all of the internal standards has dropped in sensitivity because of some high matrix in the samples. So if the internal standard has been reduced by maybe 10 or 15%, the processing of the results will just apply an additional 10 to 15% correction to the results to increase their value and correct for the matrix effect. As part of a quantitative analysis, a number of quality control parameters have to be in place to make sure accurate results are reported. So in order to verify the calibration standards, we use a different standard with the same elements to check if the calibration is correct, if we haven't made any dilution errors. In order to verify that there is no matrix effects, interference removal with helium collision gas is correctly done, and we've chosen the correct internal standard. We spike a sample with a higher concentration of each analyte to see if all of the spikes can be recovered. In order to verify the sample preparation process, for instance, where we've got a plant or a biological or a rock sample that's been digested by microwave digestion, we prepare a sample blank as well as a certified reference material that has been processed in the same way as all of the samples. This is very important to ensure that the sample preparation process extracted all of the analytes efficiently. We also include duplicate samples, and we run control checks every 10 or 12 samples to ensure whether any drift was present and whether our internal standard could correct for the instrument drift. Once all of the data has been processed and checked for accuracy, it is exported as an Excel sheet to the researcher. If you have any questions or suggestions about the presentation or our service in general, here's the email address for both me and my colleague Charney Small. Please email us your questions.
For more information on Central Analytical Facilities, please visit the SAF website and like the Facebook page. For weekly info on our ICP XRF unit, please check out our LinkedIn page. We wish you all the best for your work ahead.